Okay, so welcome everyone to Science in the Kitchen. Tonight's talk is going to be on baking beer and bananas. Just some quick housekeeping. If any questions come up during the talk, if you could save them for the end or type them in the chat, we can address them to the speakers at the end. So my name is Lauren Maceda. I'm the coordinator for tonight's talk. My job is to introduce the speakers and give us a little bit of background on what we're going to be talking about. All right, so tonight's speakers. First, we have Miley Tran. She's a researcher in the Yale Cell Biology Department. Her research is on protein sorting and secretion at the Trans-Golgi network. And a fun fact about Miley is that she feeds colleagues with baked goods, but she also feeds birdies to the Yale badminton team as a coach. And our next speaker is Anthony Eisenhower. He's a researcher in the Cell Biology Department as well. His research is on nuclear integrity and innate immune signaling. And a fun fact about Anthony is that he likes to go rock climbing. And then our third speaker is Samantha Pagan. Samantha is a researcher in the physics department at Yale as well. Her research is on experimental nuclear and particle physics. And a fun fact about Samantha are that her favorite things to bake are biscuits and bagels. All right, so now that we've met our speakers, I'm going to give us a little bit of background on what we're going to be hearing about. So when you hear the word science, what comes to mind? You might think of test tubes. You might think of big fancy laboratories with lots of equipment. And you might think of scientists researching in the lab using all sorts of fancy instruments. So here we have a picture of one of our own speakers tonight, Miley. Here she is in her lab using a pipette. So these are some things that might come to mind when you think of the term science. But did you know that scientific processes are also involved in baked goods, beer, and bananas? So to give a little context on what I'm talking about, it's first important to understand some core terms. So first, all of these things, baked goods, bananas, beer, honestly, everything in the kitchen, everything around you is made up of these tiny things called atoms. Atoms are the smallest individual units of matter, and everything around you is made up of atoms. Now we have names for different types of atoms. The different atoms are called elements. So here we have 3 elements, hydrogen, carbon, and oxygen. These are going to come up a lot in tonight's talks, and these are just different types of atoms. And then we have molecules, which are when 2 or more atoms come together to form a structure. And again, everything around you, anything that you can touch, pick up, is made up of molecules. And the way that we write molecules is we write them out as a formula. So this is the formula for a molecule called glucose. We can see that there are 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. This makes a molecule called glucose, which you can find in sugar. So when you add sugar to your coffee or sugar to your cookie recipe, you're adding in lots and lots and lots of glucose molecules. And then one last concept I'll talk about is that of a chemical reaction. So here we can see there are different molecules that are rearranging to form new molecules. And in your kitchen, this is what happens anytime you cook or bake something. Molecules get rearranged. You might start with a wet dough and end up with a nice baked cake or some cookies. There's molecules being rearranged, and that's basically a chemical reaction. So these are some things that you'll hear about our speakers talking about in tonight's talks. So to go over, first we're going to hear from Miley. She's going to talk about baking, and her talk is called Let's Bake with Science. And then we're going to hear about beer from Anthony Eisenhower. His talk is Brewing and Breaking Down Beer. And then last, we're going to hear about bananas from Samantha. She is going to talk about the nuclear physics in your kitchen. And with that, I will hand it over to Miley.
Okay, thanks for the nice introduction, Lauren. I share my screen now. And you are familiar already with this picture of the kitchen, and I'm very pleased to start this talk with science in baking. So as you might see from this picture, I'm mostly interested in these 2 things. So today I will talk to you about the science behind the ingredients that we use to make like cookies, cakes, and also breads like this one. So next time when you see a recipe online, you want to adjust it, then probably you can think about the science that I told you about and bake with science. So let's get started. So baking is very amazing. It's for me very therapeutical, and it's actually everything that you see here in the same way. So all of these different bakes I've made like in the last couple weeks or months. And the interesting thing is they have all the same ingredients inside, but they're very different in texture and their taste. So they can be sweet, savory, tender, or airy, soft, crispy, or even light. And the ingredients that you see here inside, they are added in different ratios into the bakes. And these ratios define actually what type of bake you have. So whenever I'm invited to a party or a gathering, I like to bring something baked because it's easy to adjust to whatever occasion you have and to the taste of the people that you want to give your bakes to. So imagine you are invited to a gathering, you want to bring something to bake. You first have to think about what kind of bake you want to bring. For example, cookies or cakes, or maybe pastries, or maybe breads. And all of these have the same base. So first of all, you have to think about what is the basic ingredient that all of these have in common. And this is flour. So there are different types of flour on the market. Here you can see a picture of the flours that I have at home. More specialized flours like almond flour or glutinous rice flour, but also very common all-purpose flour and bread flour. So the flours that you find in the baking section in the grocery store are all-purpose and bread flour, which are defined as gluten-rich flour. And this is more clear when we look into what is inside this white powder. So flour is made of mostly starch for 75%, but the gluten part makes up in the 12% of the protein. So actually this 12% that you see here is generally speaking protein, but most of it is gluten. And the amount of gluten that is inside here, so the amount of gluten of the protein, defines whether it's all-purpose or bread flour. Bread flour, for example, has a higher amount of gluten, so like 12 to 15%, while all-purpose flour or even cake flour has a lower amount of gluten. And why is that? This is clear when we look into the gluten itself. So gluten is a protein, and a protein is similar to what Lauren told you, a molecule, but it's like made of a lot of different molecules. So it's like a macromolecule because it's very big. And gluten itself is made up of two other proteins, which is gliadin and glutenin. Proteins can have a different three-dimensional shape. So gliadin likes to form spherical structure, while glutenin likes to have a more elongated shape or rod-like shape. And together, in the presence of water, it can form a network that is called gluten. And this network actually gives you this chewiness of a bread, for example. So bread flour has a lot of gluten, that's why it's more chewy. While in cake, you want to have a very airy and fluffy texture, and that's why you have less gluten. And you can control this by the addition of other proteins as well. So what about people that cannot eat gluten? Fortunately, there are a lot of gluten-free flour on the market now, which amazingly look very similar to gluten-rich flour from the components. So the main difference is only in the protein part, which is obviously absent of gluten, but has additives and other proteins. So additives, for example, xanthan gum, which is not a protein, is used to mimic the texture that you would get when you usually have bakes with gluten. So this chewiness. And because companies want to have some amount of protein for nutrition, they add other proteins, for example, milled beans or chickpeas. So when we talk about gluten-free flour, there are bakes, for example, macarons, that are made of almond meal, which is technically speaking gluten-free flour because it does not contain gluten. However, almond meal is just milled almonds, and therefore, when you next time want to substitute gluten-rich flour for gluten-free flour, I would not take something like almond meal, but look into the composition if it's roughly similar to gluten-rich flour, just without gluten. So let's say for the gathering, you want to bring cookies. So cookies can be very different and adjusted to the taste of how you like it. So let's say we have like two types. Either you have like tender or crumbly and soft cookies, or you have the more chewy kind of cookies with a crispy bottom. If you look for recipes online, you see that the tender cookies mostly have only egg yolk and white sugar and a high amount of butter, while these chewy cookies have a ratio of brown sugar and white sugar, uses whole eggs, and compared to the butter part, it's a little bit less than to what you find in the recipe of tender cookies. So this is due to what these ingredients do in the dough. So sugar and eggs not only contribute to the taste, but also to the moisture. And what you maybe already know, butter is the main contributor of fat. So let's see what sugar does. So obviously sugar adds sweetness, but it also influences the structure, texture, and moisture of your dough. So as Lauren already showed you, the sugar that you find in the kitchen is looking like this chemically, and it's called sucrose. It's a combination of glucose and fructose, which looks chemically like this. So you have a hexagonic carbon ring for glucose and a pentagonic for fructose, which are bound in the middle. But this is not important for us here. For the rest of the talk, I will use this icon when I talk about sucrose, where you can see the glucose and the fructose bound in the middle with this little U. So back to our cookies. So let's say we want to make tender cookies. What does the sucrose do? So on one hand, sucrose, like white sugar, will bind water. And that actually leads to a competition with gluten because gluten, as I told you, needs water to be formed. So this leads to a formation of a weaker gluten network. So it's less dense and it's more soft. On the other hand, white sugar is solid crystals, and during creaming, which is the mixing of solid butter and white sugar, air is incorporated. These air pockets are stabilized due to the butter and due to the granulation of the sugar. And this gives a lift into your cookies and also makes the cookie dough less dense. So there are many forms of sugar. White sugar and brown sugar I already told you about. They are actually used in different cookie recipes, but are chemically speaking very similar to each other. Sorry. So both of them contain a high amount of sucrose, that's why it's here in bold, and a lower amount of glucose and fructose. However, white sugar, what I already told you, will bind water, and then it will bind the water actually in the dough. So the dough and also the final bake will be a little less moist, so more dry. While brown sugar also binds water. However, it contributes to the moisture in the bake. How's that? It's because it contains molasses, which also contributes to the brown color in the brown sugar. So this is the residue that is remaining during the refining process of sugar cane. And due to its attractive to water, it gets the water from the air. And then when you add brown sugar to your dough, it actually adds also the moisture into the dough. So when you want to bake something with more moisture, just add brown sugar. Other sweeteners, for example, liquid sweeteners, are honey, which are very popular. It is a simple sugar solution which contains also vitamins and minerals. It has a high amount of fructose and is therefore easier to digest. Other sweeteners are, for example, fruits. And there, bananas are very popular to use in baking. They contain a high amount of glucose and fructose, are very sweet when they are ripe, but also have a high starch content. That's why you cannot one-to-one substitute white sugar with bananas. So now we talked about how white sugar and brown sugar adds to moisture. Now let's look into the difference of adding only egg yolk and a whole egg. So eggs contribute to the taste and color, but also to the stability because they are a combination of fat and water. So let's look into egg. Egg white is most of it water and to 10% protein, while egg yolk is mainly fat and also the color-giving compound. When we bake with eggs, we often do use egg white and beat it with white sugar to get a meringue. And this process, this aeration, is in baking terms also called leavening. When we want to have a rich, soft, and tender bake, we often add more yolks. And this is a similar way how fat will contribute to this. So butter enriches, tenderizes the dough, but also contributes to the leavening and stabilizes the final bake. This is due to its property as an emulsion, which is the mixture of two or more liquids that normally don't mix. This gets clear when we look into butter, which is actually milk fat droplets in water. So at room temperature, butter is solid. And this is used for cookie dough chilling. So usually you chill a cookie dough in the fridge, make it even colder so the butter even more solid. So this contributes to a reduction of the spread of the cookie dough when you add your cookie boards on the baking sheet. And this stabilizes the shape. This also stabilizes the shape of cake layers, for example, because you store them at room temperature. And then these wedding cakes that are very heavy, they have a high amount of butter. So they can also be very stable. In melted state, butter will coat flour particles, and this will influence the gluten network because it will cause a reduction of the gluten network. Since gluten cannot get water and also is coated with the butter, the final bake will be more soft and tender. So butter is also used when we want to make pastries. And interestingly, pastries, for example, eclairs are very different from their texture. They are crispy and airy, and most pastries are also very fine and delicate. This is because baking with butter works like the following. So the high temperature of the oven evaporates the water and creates air pockets that are then coated by the residual milk fat. In a process called lamination, which is generally speaking the technique to generate multiple layers to improve the properties of a certain product, in baking terms, this is the repeated rolling and folding of butter to create ultra-thin dough layers. These dough layers you can see in a cross-section of a croissant, for example. There you have like big air pockets that are divided by very, very thin dough layers. And this is achieved during the chilling process after each rolling and folding. So you always have like a solid state butter and then a very thin layer of dough. So you prevent the mixing of the butter into the dough. So I talked to you about how we get a lift into bakes. So how we get air into, for example, by making meringue, so beating egg whites and white sugar, for example, this is used to make macarons. Or by creaming butter and white sugar together to stabilize cake for lifting or also give a lift into cookies. But there are also bakes that need a little bit more lifting. For example, bread or cupcakes and also additionally normal cakes. So there we use another gas, carbon dioxide, which is naturally produced by yeast and chemically by baking powder and baking soda in the chemical reaction. Sodium bicarbonate, which is the main compound of baking soda and also found in baking powder, reacts with acid and forms carbon dioxide and water. This carbon dioxide is a gas that will lift the dough. So baking soda is pure bicarbonate. That's why you will need to add an acid into the dough, which is achieved by adding, for example, vinegar, fruit, or even yogurt. Baking powder, on the other hand, already contains the acid in its formulation. That's why it only needs heat and moisture. Yeasts are completely different. They are living organisms, and the baking yeast, Saccharomyces cerevisiae, looks like this. So one of these tiny little guys is compared to a sugar crystal. Only 1%. So that means that you need 100 of these to form one tiny little sugar crystal when you look at the size. So how are these little guys helping us with getting carbon dioxide into our bake? So also this is based on a chemical reaction that you can see here, where the yeast actually eats sugar and water and convert it to carbon dioxide and alcohol. And since this alcohol is formed, this process is also called fermentation. So when we bake with yeast, we have three options. Either we use instant yeast, which does not need any activation, dry yeast, which are dormant, so they are sleeping. So when you add warm water, you will wake them up and activate them. We also have fresh yeast, which are actually the yeast that I showed you before in a compressed state. They are perishable, but they are also most active. So I talked to you about cookies and pastries. Let's go over to bread. This is what we mostly think of when we talk about yeast. And when we talk about yeast bread, then very popular is sourdough. Sourdough is a little bit different from what I told you before when it comes to yeast. We have here wild yeast and also lactic acid bacteria. Wild yeast can only digest simple sugars, while lactic acid bacteria helps the wild yeast by digesting more complex sugars. When you have your sourdough, you always need to discard part of it to remove excess alcohol or also dead yeast cells. Also, you have to add fresh nutrients like fresh flour and water. Lactic acid bacteria helps it a bit because it feeds on dead yeast cells. And these two together make up the properties in sourdough. So a dough that is easier to digest because it's pre-digested and also has a sour flavor from the lactic acid. Another term that often comes up with sourdough is leaven, which is just for you to know the pre-ferment mix of a sourdough starter with fresh flour and water. And this is used to give an even more enhanced rise or to change the flavor a bit. So when we think about something to bake, we have to decide what type of leavening we want to take. And this is very important to achieve the results that we want to have. And therefore, we need to decide on the chemical properties. Baking soda and baking powder, for example, can be used immediately because they react immediately. They are strong leaveners. That's why they're very good for baking with fruits because fruits are heavier. They're also good for quick breads, like banana bread, because they react immediately. Yeast, on the other hand, often needs activation with sugar and warm water and have a very slow but consistent rise. And this is actually good for breads where you have a lot of gluten formation because they also form in a more consistent way. So when you bake a bread with yeast, it's less likely to collapse. Also, yeast taste is a little bit more pleasant than baking soda and baking powder. So today I've told you about how the taste type and the texture of your bake is influenced by these 5 ingredients that you see here. So how flour has gluten and this will add to the chewiness. How white sugar differs from brown sugar and how eggs add moisture. Also, how butter tenderizes your bake by weakening the gluten network. I also showed you how fruits like bananas can be used instead of sugar, but have a different property, so you have to be careful when you want to use a banana completely instead of eggs and butter as well. Also, I mentioned leaveners, baking soda, baking powder, and most importantly, yeast, where we use as baker the carbon dioxide that they produce. But in the next talk, in the fermentation reaction, we use the alcohol, or better, Anthony uses the alcohol for making beer. So let's talk about that.
Thanks, Miley. And I'll start our next portion of our talk tonight. I hope you guys are all enjoying it so far. I know I am. And so for my portion of our talk tonight, I'm going to talk about the brewing and breaking down of beer, how it's brewed, how our bodies break it down, and then the unfortunate aftermath of hangovers. And so my portion of the talk today is going to talk about how beer goes from the brewery or kitchen, in my case, where I brew beer in my own house, which is much closer to how it's been done thousands of years ago, but both making in the brewery and the kitchen follow the same key steps, and how that beer goes from the brewery or kitchen to a glass, and then and through our bodies once you drink it. And so to start off, I'll kind of introduce the main ideas of beer making. To start, for beer to be beer and not another type of alcohol or another beverage, is there's 4 main ingredients required to make it. The first would be malt, which is roasted grains such as barley. And this is the main producer of the sugars, colors, and flavors of your beer. As you can see here in this image, there's 3 different colors. Those are different roasts, and those heavily contribute to the color of a beer and the flavor. So for example, a really light one, you might get something more like a Pilsner or a Heineken, and these really dark, more darkly roasted malt might be something more like a Guinness or a stout. The second main ingredient in beer is going to be your hops, which is this plant right over here on the right. Hops are known for kind of giving a hoppy or bitter flavor to your beer. And they're also really important in helping create the foam you get at the top, which I at least enjoy, and I hope others do as well. The third ingredient that's really important is yeast. From here, you can see both the same picture of Miley's yeast as well as yeast we use in my own lab. And the yeast do the most important job of making beer alcoholic so that you get the fun part of it. And the fourth and final ingredient of beer that's really important is the water, because that's how you get a nice big liquid to drink. And conveniently, similar to there being 4 main ingredients in beer, there's also 4 main steps to brewing. The first step is the brewing, but this is more like the way that you would brew tea, which I'll go into a little bit more. The second is the fermenting, which is where the yeast take over and do their job producing the alcohol. The third is called aging, which is what happens with a lot of alcohols, including wines and whiskeys, where you give time for some other flavors to develop in your beer. And the fourth is bottling, and this is most important for creating the carbonation in a beer, because I don't know about anybody else, but a flat beer with no carbonation just doesn't taste the same. And so the first step of brewing. So the way that I like to think about this is similar to making tea. The role of brewing is to use heat and hot water, just like in tea, to release the sugars and flavors from the other ingredients, in this case, the hops and the malt. And so your first step would be to boil the water. And then using that hot water, you're going to steep the malt and hops for a long time to break down all the material and release the sugars and other chemicals that make beer flavorful. Second is the fermenting. And so on the right, you'll see this big 5-gallon container. This carboy contains a big vat of that grain tea where I've removed all of the grain from it from my own kitchen. And so fermenting is the step where we're going to add yeast to this container, seal it, and let the yeast do their job. So this step is to use the sugars that released from all of that malt and hops as fuel to make alcohol. And we use them as machines to produce that alcohol for us. This step is really important for having a closed environment, so that the only thing that's going to grow in this container is the yeast that we add, and not any of the yeast or bacteria that are floating around in the air. Historically, when beer was first being made thousands of years ago, they used wild yeast in the air to ferment beer, but as time's gone on, we've kind of refined and picked and chose the yeast we want that do their jobs the best and create the flavors that we like. And so I'll talk to you guys a little bit about the sciencey part, the yeast job during fermentation. Again, we're going to go back to our friend, the budding yeast, or baker's yeast, or brewer's yeast. Those are all different terms. Budding yeast is the term we use in the lab when we're using yeast as a science organism, up here on the right. And as Miley already talked about, it's used in both bread making, baking, and beer making. And it uses the same chemical reaction, but we use them for 2 different purposes. We're using those little machines, eating all of our sugar hexagons that Miley showed you earlier to produce not only gas, but in our case, the beneficial part is ethanol. And ethanol is just one type of alcohol. Alcohol describes a variety of different molecules. However, the alcohol that we all drink is all ethanol. Other alcohols can be poisonous. So if you hear me saying alcohol, you're going to want to think just ethanol, because that's the one that we drink. The third step of making beer is called aging. And in a non-hoity-toity way that allows for flavors to develop in your beer. And what that really means is that in this container, now that we've let the yeast do all their fermenting, they've eaten up all the regular sugar that they eat to produce that alcohol and carbon dioxide, but there's lots of other things floating around in there still. And so the yeast can actually, because they want to stay alive, will start to eat the more complex sugars or the other molecules floating around, and instead of producing ethanol and carbon dioxide, we'll create some of the other flavors that contribute to different beers tasting differently. And I'll give you a couple examples of some of the molecules that can give beer some of these other flavors, using a glass I have at home as an example. And so one of those molecules is called isohumolone, which is this big, long structure you see here. It has 21 carbons, 30 hydrogens, and 5 oxygens. So if you compare that to the glucose molecules that we've seen earlier, this is like 4 to 5 times bigger. And so this molecule comes from the hops that we've added. And this is the molecule that gives you that hoppy flavor or bitter flavor that comes from hops, that's especially prevalent in things like IPAs. Another example of a different molecule is called dimethyl sulfide. That's this molecule down here. It has a couple carbons, some hydrogens, and it has a sulfur, and that's one of the big things that differentiates it from sugar. And this smaller molecule is found in a higher amount in things like pilsners and lagers. That it gives it a fullness and a roundness to that lighter beer. And so, to me, the most important step of enjoying my beer is the bottling step. This is what happens after aging. And the bottling step is to get carbonation in your beer so it's nice and bubbly and tasty. For example, for context, these 48-ish beer bottles you see down here are the 48 bottles that came out of that 5-gallon picture of the brew I've been taking you through so far in my own kitchen. We just finished bottling, the bottling process finished a couple weeks ago, and we just got to try it, and it came out really nice. But the bottling process is to carbonate the beer. And commercial factories will take a really easy approach, and they'll use a big fancy machine and just inject carbon dioxide into the bottles and cans and seal it so that it has a very specific amount of carbon dioxide, and it's really easy, and then the job is done. But home brewers like myself will take advantage of the same reaction we've been seeing all night so far. And we'll add actually a little bit more sugar to the beer before we bottle it. We'll bottle it, and then now that it's sealed, the yeast will take that little bit of sugar that we added. They'll produce a little bit of ethanol, but not enough to really change how much alcohol is in the beer. But now that the bottles are sealed, they'll produce carbon dioxide, which will get trapped in the beer. And so when you open it, it'll have carbonation. And so I hope so far in this talk, you've understood a little bit more about how beer is made and the role of yeast and some very important chemical reactions in creating the flavors and textures of a beer that you know and love. And I'll spend the next part of my talk kind of talking about how the alcohol gets broken down in our bodies and why that tends to lead to hangovers and the less fun part. So the first is why do we need to break down the alcohol, the ethanol specifically in our bodies? And that's because, like many other molecules, our bodies, just like the yeast, will have different uses for them. And unfortunately, alcohol such like ethanol, our body doesn't have good uses for, and it tends to actually cause harm to our cells. You may be familiar with this with things like alcohol poisoning and overdosing. And so alcohol can do mainly impacts 3 parts of the body. It can damage the liver. The liver is where alcohol is broken down, and I'll get into a little bit more in a few minutes. It can damage the brain, and that kind of makes a lot of sense if you think about the fact that, like, when you drink, you get a little bit buzz, you know, your brain just starts to feel a little bit more loosey-goosey. And so the relationship between alcohol and the brain comes across pretty clearly. And the third would actually be damaging the gut. Most directly, you can think about like the fact that a lot of people get nauseous after drinking and things like that, but also it can have longer-term effects. And so where is alcohol broken down in the body? Well, you drink beer or other alcohol that goes through the stomach. And unlike food, which continues through the stomach into your intestines and then out of your body, alcohol is actually absorbed through your stomach lining and goes into your bloodstream, which is why this is a lot faster than eating. And so taking shots can get you drunk a little bit faster because it goes to your bloodstream faster than like eating does. And then eventually it travels to your liver, where your liver does the job of breaking down a lot of the toxic chemicals in your body so that you remain happy and healthy. And so how do we break down alcohol? Breaking down alcohol is similar to a lot of the chemical reactions we've shown before, where it's taking one molecule and rearranging it to get other molecules, and in this case, breaking down it, rearranging them into smaller molecules that our body is happy with. Our bodies have developed to break down alcohol in a 2-step process. First, you'll have ethanol, and with the help of an enzyme, which is like another little machine, ethanol will be converted to acetaldehyde, which is a smaller molecule. You can see it has less carbons. And then it will be broken down by a second enzyme to produce acetate, which is a molecule our body is happy to use for many processes. And so these two little enzymes do that job for us. But while I've already talked about kind of how alcohol and ethanol is poisonous to you, it's toxic. This second byproduct, acetaldehyde, is actually 10 to 20 times more toxic than ethanol, which is why our bodies have developed this two-step process to break it down one more time into the acetate that doesn't harm us. But I think what's kind of interesting thing about acetaldehyde is that some of you are probably familiar, as I am, of some people when they drink will actually flush and turn really red. And that's actually because this enzyme right here, in some people, is slower at doing its job, which leads to a buildup of this acetaldehyde, and that's when you flush. And so starting to talk kind of about the negative repercussions and what happens once you start breaking down alcohol, I think that nicely transitions us to talking about hangovers. And so what is a hangover? I'll give you the nice, gross, technical definition, where it's a combination of mental and physical symptoms that you experience the day after drinking, once the concentration of alcohol in your blood is 0, meaning that your body has broken down all the alcohol in your body. I think of it's, most of us are probably more familiar with thinking of a hangover as things like headaches, nausea, tiredness, fatigue, dizziness, etc., which is really, those are all the symptoms that this definition up here is talking about. And so, well, I've talked a little bit about how ethanol and acetaldehyde are kind of, they're poisonous, they're not good for you. Those are the main chemicals that are causing hangovers. Your body just, both acetaldehyde and ethanol are just, your body, they can break them down and deal with them, but like as you see from hangovers, sometimes it takes a little while, and your body will start to hurt before it gets better. However, as you might know from drinking different types of alcohol, you don't always get a hangover, which has a variety of causes. But one really includes a lot of the other chemicals and molecules in the things that you're drinking, which also tend to influence the taste. So for example, tannins are a type of molecule that have been shown to cause worse hangovers. And you see them a lot in red wines, and that's also might be why some of you might be familiar with the stereotype of red wine might give you a worse hangover than white wine. But they're also very important for creating that that dryness you get in a red wine. Those are from tannins. And similarly, sulfides are also known to worsen a hangover, but they're also really important for the flavors of things like beers, where you get a lot of dimethyl sulfide in a Pilsner that creates that fullness. And so I think what's really cool and important coming out of this kind of scientific knowledge that we found that some of these chemicals can worsen your hangover, they also happen to make things taste better, is gaining this knowledge about kind of there can be a trade-off between chemicals that do things that are good for you and taste good, but also happen to do something bad for you. But that your body has ways to deal with that. And so I hope from my portion of the talk, you've been able to understand how beer goes from the brewery and kitchen, in my case, to a glass and through our bodies. And to kind of wrap up the chemistry portions of our kitchen talk, I hope that the next talk will be really interesting because it's going to go even smaller scale than molecules into those individual atoms throughout the kitchen, and how we interact with them, by Samantha.
Yeah, thank you so much. I will just share my screen and we'll get started. Hi, so yeah, I am Samantha, and this talk is the nuclear physics in your kitchen. And as we just heard from our previous two speakers, we heard a lot from Anthony about how all of the science is happening in beer making, and then from Miley about baking various things like bread. So for my talk, we're really going to transition more into physics and talk about the nuclear physics in your kitchen. And what I hope you gain from this talk is just that nuclear physics is really all around us. You see some examples here that we're going to go through. And I also hope you get a new lens to terms like nuclear decay and radiation, which will be some of the things that we're talking about today. So to start off, I study particle and nuclear physics, and I feel like when I tell people that, the first questions I get are something like nuclear power or weapons. And if that's where your brain went, I completely understand if you don't want me near your kitchen, you just kind of want me to get out. But I will tell you that a lot of the things that I think about day to day aren't really those questions, but they're a lot more about very low level kind of background events in nuclear physics that are happening all around us, basically in any environment that we go to. So we call this background radiation, and it's even happening in your kitchen, which is going to be what we're focusing on today. So for the first part of this talk, we could go to lots of different places in your kitchen where nuclear physics is happening, but let's just think about bananas for right now. And bananas are a really rich source of potassium, and a small amount of this potassium is radioactive. And kind of understanding all of that is going to be the first portion of this talk. So to start off, just a quick crash course on what is nuclear physics. So when I say that, what am I talking about? We can start with the periodic table of elements, and in baking and beer making, we've been talking a lot about carbon and oxygen today. Potassium is also an element, and its symbol is K. You're going to be seeing that a lot. And a singular unit of an element is called an atom, as we've already talked about. And atoms actually have a structure within them. So in the center of atoms, we call that the nucleus, and that is made of neutral particles called neutrons, positively charged particles called protons, and then orbiting the nucleus are negatively charged particles called electrons. And as you might have guessed from some of the names, nuclear physics is really concerned with what is happening in the nucleus of atoms and how to describe what happens there. So another really important concept for understanding what's happening in a banana is this term called isotope. And what an isotope is it's just a form of an element. And elements are basically named by the number of protons in the nucleus. So if we have a potassium element, it has 19 protons. But what can vary is the number of neutrons in that nucleus. So this top number 40 is actually the number of protons plus neutrons, and it doesn't have to be 40. So other potassium isotopes that you can find in a banana are potassium 39, 40, and 41. And really something that these different isotopes can influence are whether an atom is stable or unstable. And the next little bit's going to explain what I mean by that. So first, we'll start talking about what nuclear decay is. And nuclear decay is a spontaneous process. It's random, and it's what happens when unstable nuclei decay to a different form, and then they release energy. And this energy you can just think of as radiation. So an example of this is when a neutron in the nucleus decays to a proton plus an electron plus a neutrino, and that's the last time we'll talk about this particle, plus energy. And nuclear decay is actually happening in bananas. So this is happening in a potassium isotope. And this is because potassium 40, which we talked about a little bit earlier, is actually radioactive. So a really small percentage of potassium in a banana and on Earth is potassium 40. You can see it's about 0.01%. And the rest of potassium 39 and 41 mainly are stable, so they don't undergo nuclear decay. And the actual decay that's happening is happening with potassium 40. And it's the same decay we talked about. So it's when a neutron decays to a proton plus an electron and energy. But what's actually happening in a banana is this time a neutron in the potassium 40 nucleus decays to a proton. And that means that that nucleus actually gets an extra proton. So it's not potassium anymore. It's calcium because it gained a proton, so it's a different element. And then the radiation that comes out are these energetic electrons. So you can basically think of this as if you had bananas, these electrons with energy would be the radiation that's coming out. And another important idea is how often this is actually happening. So a concept from nuclear physics to describe this is called half-life. And half-life is the time needed for half of the original samples to decay. And we will walk through what this means, but the half-life of potassium-40 is really long. It's over 1 billion years old. And half-life is something that we call an exponential decay function. So maybe you've heard of exponential growth, the way that things like viruses spread, but this is exponential decay. So if we started with, let's say, 100 potassium-40 atoms, we'll call this N0, the number that we start with. If we wait one half-life, half of them are gone, so we'll have 50. If we wait another half-life, half of those are gone, so then we'd have 25 atoms. And then if we kept going, it would be the same thing, just multiplying by a half every time to get the number that you have at any given time. So we can make actually a function out of this, a math function, and you see that the number you start with times by 1/2 for every single half-life is this function. The rest of this is just showing you that you can use math. So basically what this does is it says we get an extra half every time that we reach T1/2, which is a half-life. And that's how we describe half-life. And if you've ever seen this written a different way, don't worry too much about this next line, but we can define things in different ways using math. And here you actually get an E and an exponential if you've ever seen that and kind of relate it to exponential decay. But these are all the same functions that we talked through. And actually what I wanted to do next is ask you all what you think. So I'm posing the question, how often do you think potassium-40 decays in a banana? And just to recap a couple of facts, about 0.01% of potassium is this radioactive potassium-40. The half-life of this is over 1 billion years old. And I'll give you the extra fact that potassium makes up less than 1% of a banana by weight. So I'll just give you a few seconds if you want to think to yourself or even type in the chat how often you think this is happening in one banana. Okay, so the actual answer is this is happening about 15 times every second in a banana. And if all of those numbers adding up, that's way higher than you think it might have been. The real key to this is just that atoms are so small and there are so many atoms in a banana. So this is the amount of potassium atoms in a banana is how we actually get those 15 decays per second. So now I want to talk a little bit about what that actually means for us in terms of like, what does this radiation do? And for that, we turn to a concept called effective dose. And this is really how we measure the effects of radiation. And it depends on the kind of radiation. We've mainly been talking about just one type right now, the amount of radiation, and also how it affects different parts of your body. So radiation to something like your fingers is very different than radiation to like internal organs that are more sensitive. And a unit that I found to talk about this that I really like and that I'm going to use for this talk is actually the banana equivalent dose. So this is something that scientists came up with to talk about very, very tiny doses. So really infinitesimal doses that we can find. And it's the dose of radiation basically in a banana. And we could use different units to talk about this. So there are scientific units we could look at instead, but for the rest of this talk, since we're just talking about these super low levels of radiation, we're going to stick to banana equivalent doses. So to give you just a sense of how these doses scale, if we start at the bottom with 1 banana equivalent dose, something that's very small, bananas are normal in our kitchen all of the time, we can look at some other doses that are around us. So every year, just by kind of existing and with all of the background radiation in our lives, we get about 60,000 banana equivalent doses, so on the order of like 100 a day. If you were to get a full CT scan, which is one of the higher radiation like medical scans you can get, and you would totally get this if you needed it would be around 100,000 banana equivalent doses. And these are all on the order of like normal doses that we interact with in our lives. If you go a couple of orders of magnitude up, these are where you get doses that can have really negative effects and are quite dangerous. So if you went up to 10 million or 40 million banana equivalent doses, these are things that cause like radiation sickness and even lethal doses. This is what happened in Chernobyl to people who got sick from that. And then if you go even higher up to 1 billion, that's actually the kind of doses that we apply really in a very targeted way towards cancer tumors to kill only those cells and make sure that the cancer dies. So now I wanted to go through and just give you a few more like quick examples of this background radiation in your kitchen, not just in bananas. So for that, we can actually turn to bread or any of the baked goods that we've had, as well as the yeast in the bread and even beer. And this is because there's carbon in all of those things, as we've been talking about. And there's actually a form of carbon called carbon-14 that also undergoes nuclear decay. So about 1 carbon atom in a trillion is carbon-14, and its half-life is smaller than potassium-40. It's about 5,000 years. But the decay that's happening is pretty similar. So you can see here carbon-14 decays to nitrogen, which is a gas that's all around us in our atmosphere, and then this energy and an electron. And if we took 1 packet of yeast, this would be happening about every 5 seconds. Some other examples, so if we look to other foods in the kitchen, so imagine that in this bowl is a bowl of Brazil nuts. There's also foods that have some of this background radiation. Brazil nuts are really famous for being good at absorbing minerals from the soil, so they're quite rich in some minerals. But when they do that, they also absorb trace amounts of lead and radium, which have radioactive isotopes. So eating 2 Brazil nuts is about the equivalent to 4 banana equivalent doses. And finally, we can look at places in our kitchen for some other sources of background radiation that aren't just in food. So if you have granite counters or any type of like rocks in your floors, there's trace amounts of uranium and thorium that are pretty ubiquitous and can be found all around us that are contributing to this. And then pretty much everywhere on Earth, there's something called cosmic radiation, which is radiation from the sun and our solar system that comes in and it interacts with our atmosphere and creates kind of this shower of particles that's even coming into our kitchen. So I hope what you've gained from this talk is on the level of what's happening in nuclear physics and even a bit of particle physics, what's happening in your kitchen. So these are all examples that we've talked about, and you can see it's really all around you, everywhere you look. And then earlier in our talks, more on the level of what is happening with chemical reactions, so reactions between molecules. You heard a lot about what's happening when you make beer or bake something in your kitchen. And we hope that what you're taking away from our talk, one of the main things is that whether you're baking or you're eating a banana or enjoying your favorite beer, science is really happening all around you, everywhere you look. And that this is, science just in the same way as test tubes and pipettes and chemicals are also science as well. It's everywhere you look. So I think with that, we will move to the questions portions of this. And before we do that, I'll also just flash up some extra information and links we have if you want to take a screenshot of it or go to these sources later.